Pascal's triangle. In Pascal's triangle, each number is the sum of two numbers directly above it. For example, the second element of the fourth row is 3, which is equal to the sum of 1 and 2 directly above it. You can verify the same for other elements as well. The problem is to find the element at row R and column C where R and C starts from 0. The solution is that the value at position RC can be calculated using the combination formula NCR, where n equals to R and R equals to C. The combination formula is NCR equals to n factorial divided by R factorial into n minus R factorial. So our problem is reduced to calculating the factorials, but there exists a more efficient way to calculate NCR instead of calculating and dividing factorials. Since there is an n minus r factorial in the denominator, we can expand the n factorial of the numerator up to n minus r factorial. The n minus r factorial is cancelled from the numerator and denominator, resulting in this. It can be coded as, starting with 1, at each step we multiply by n minus 1 and divide by I plus 1. The time complexity is OC, where C is the given column number. Find next permutation. Find the next lexicographically greater permutation of an array. If not possible, return the array sorted in ascending order. Example, given 132, the output is 213. Another example, given 321, the output is 123. A brute force solution would involve finding all possible permutations, searching for the input in those permutations, and printing the next permutation. The time complexity would be very high, n factorial time n. There exists a linear solution to this problem. Let's understand the algorithm with an example. Imagine we have the input array 42531. First we need to identify the breakpoint, which is the last index where an element is smaller than its next element. In our example, as we traverse the array backward, we find the breakpoint at index 2, where 2 is smaller than 5. Now since a breakpoint exists, we proceed. We look for the smallest number in the right half of the breakpoint that is greater than the element at the breakpoint. In our case, it's 3. We swap it with the element at the breakpoint, giving us 43521. The final step involves reversing the right half from the breakpoint index onwards. After the reversal, our array becomes 43125. The algorithm can be coded in Python as this. It first identifies the breakpoint, which is the last index where an element is smaller than its next element. If no breakpoint is found, indicating a sorted array in decreasing order, it returns the array reversed. If a breakpoint is found, it swaps the element at the breakpoint with the smallest element greater than it in the right half, and then reverses the right half. The result is the next permutation in lexicographical order. The time complexity of this solution is n. Set matrix zeros. Given a matrix, if an element in the matrix is 0, you will have to set its entire column to 0 and the entire row to 0 and then return the matrix. If the input matrix is 1 1 1, 1 0 1, 1 1 1, then the output matrix will be 1 0 1, 0 0 0, 1 0 1. The reason is that 0 in the input matrix lies in the second row and the second column. So in the output matrix, all the elements of the second row are set to 0 and all the elements of the second column are set to 0. We can solve this using two extra arrays named row and column. The ith element of the row list tells whether the ith row has a 0, and the ith element of the column list tells whether the ith column has a 0. We can iterate over all the elements of the matrix using nested for loops. If the element at the I, j index is 0, we set row I to 0 and column j to 0. After we have calculated the row and column list, we iterate over the elements of the matrix again using nested for loops. But this time we set the element at I, j to 0 if either row I is 0 or column j is 0. The time complexity of this approach is m into n, while space complexity is m plus n, where m is the number of rows and n is the number of columns in the matrix. There exists an even better solution in which the space complexity is constant. Instead of using two additional lists to track whether rows and columns have 0, we use the first element of each row to denote whether the row has a 0 and the first element of each column to denote whether the column has a 0. Since the element at 0, 0 cannot be used to denote whether both the first row and the first column have a 0. We use it to denote whether the first row has a 0. And we use an additional variable called 0 to denote whether the first column has a 0. The rest of the algorithm is very similar to the previous algorithm with minor changes. Like for assigning zeros, we first assign zeros to the matrix from index 1, 1 to n-1, n-1. Next, we mark first row to 0 if element at 0, 0 is 0 and set the first column to 0 if col 0 is 0. We return our final matrix, and that's the solution.